Hello everyone, my name is Fadi. Today I'll be presenting classification of Eurosat data using deep learning. Let's get started. So first of all, introduction. Eurosat is a dataset made up of a 64 by 64 RGB satellite images. It's used to classify different types of land, forests, residential buildings, industrial zones, and farmlands. And in this satellite, basically I focused on the project and I trained and compared several architectures like convolutional neural network, VGG16, deep neural network, and ResNet50, EfficientNet B0, DenseNet 121, and Vision Transformers. And so the model will train on TensorFlow using Python language on the same dataset in addition to adding techniques like data augmentation to improve accuracy. I targeted a range of like 90%, and some models did do better than 90%, some of them did worse than 90%. And also, the results showed that DenseNet 121 was the best, and ResNet 50 was also below that, and VIT was below as well, and it performed the best, while simple custom model that I created was less accurate on a CNN. The comparison added highlights on how the model architecture and design and its technique can, significantly influence the performance of the satellite images. The approach that I took was I first loaded the Eurosat RGB dataset. I extracted dataset and I put it in the TensorFlow library, and basically I resized all the images, and I took the images from directory to create a training validation dataset with an 80 to 20 split, and basically I applied basic data augmentation. So the data augmentation will be like flipping, rotating and zooming on the data set, and then also this does improve and reduce overfitting. So they trained and compared several models on this Euro satellite images, and the model I already mentioned on intro was like CNN VGG16, Deep Neural Network, ResNet 50, EfficientNet B0, DenseNet 121, and VIT. And so basically I was using the same input pipeline and the training settings that I had for CNN. Um, and also I evaluated each model using validation accuracy and loss to see which architecture works best for the URSAT. And the challenges I faced was GPU memory limits when training or fine-tuning larger models. Basically, it takes a lot of time to do that, and especially deeper CNNs and transformers. They took most of the time to train, and the longer the training time for deeper architectures compared to the simple one. Um, the simple one took a couple seconds, the longer one took minutes to train for each kind of epoch. And I'll be explaining what epochs is and what other things regarding the model as well. So managing multiple notebooks and save models also is a challenge. Sometimes overrides and stuff were missing. I had to make sure that I don't make a miss. So I was making sure that preprocessing was also consistent across all models and the comparison stayed fair. Again, basically I tried to do 10 epochs per model to stay the same and consistent. So the data inputs and design for Eurosat images were kind of resized, normalized, and lightly augmented so that the model can learn patterns more effectively. And so all the data goes through the same preprocessing. So every model is trained under identical conditions. And CNN kind of starts by learning small features like edges, textures through its convolution layers. I'll also be explaining what the convolution layers are and how the architecture plays a role on the learning model. So, so the deeper the layers, learn larger, more meaningful patterns across the image will give an accurate result. So kind of techniques that I used was kind of global average pooling to to compress each feature, map it into a single value. So this helps the model to understand the image globally, not just in a small patches. Final dense layer kind of uses the feature to predict one of the 10 land use cases, and the CNN serves as a kind of baseline to the original code that I kind of came up with, and also the other one will be kind of compared like VGG16 and so on. And so basically they follow the same idea, but they have their own techniques. So this is the code that I had, and this is the model that I created, and I'll be explaining what the convolution is, you know, pooling is, and so on. And so this is the code and how I trained it. On the bottom left, you can see the optimizer, the summary, and the history that trains on. There are 10 epochs there. There are training validations, training loss, and we have also the losses sparse categorical cross entropy. So basically, it's one of the predictions that I'll be also explaining as well. And there's a learning rate that the model learns at a speed of 0.01, which I normalize, and some different models will have different kind of learning rate. And yeah, so what is filtering? So like I mentioned, convolution 2D filtering is kind of a small 3x3 window that can slide over the image, and it takes patterns like colors, textures, and such things that can learn different features like shapes, buildings, and water around the Euroset that I had data set. So it learns basically based on that by sliding window, and the more the patterns, the more bigger, and learns slower. Yeah. So pooling pooling is kind of reduces the image sizes and also keeps the image the important information, and this also reduces the kind of overhead on the learning model. So it also helps the model focus more and has a kind of strong feature and reduces some computing to the GPU. And so what does the Atom Optimizer do here? So basically it makes the predictions more accurate and adjusts the learning rate for parameters, smoother training, and so on. Yeah. So epoch, like I mentioned, epoch is kind of it takes model sees the training data set at once, and then the higher the epochs, the model has more chances of learning, and the lower the epochs, it's basically called underfitting. So the model does not learn that fast, and when there's too much epochs, that means the model overfits, so it learns a lot, but then there's no actual kind of result, will be kind of overfitting. And so also in the code there is dropout, and basically dropout is kind of turns off some neurons during training, so it reduces overfitting to help. And so also in the code there is activation function. The activation function is kind of decides which neuron to output, and this is part of the neural network that the model has with architecture. So it helps to learn kind of nonlinear patterns on the images. So without this model activation function, then basically it will be a simple linear and not a complex model. And the activation function, one of them is kind of relu. There's different ones that are sigmoid and some other activation functions that you can implement, but the best one is relu. So this relu helps the model to learn fast and basically removes noises and then makes the training much faster and stable. And this overall reduces kind of the gradients that it has. So basically, what is softmax here? Softmax is the output to the probabilities that the highest the better kind of output that it can predict for the model. And the categorical cross entropy is kind of the prediction as well. So it's a model prediction that can um, basically the higher the prediction, it will have less loss, and the lower the prediction will have larger loss. And the more training would reduce the loss, and prediction becomes faster. So here's the figures here. This is the convolution, how it works. Based on the figure, it shows that you have some inputs in the graph, and the output is kind of the feature map that shows on the red, if you can see that. On the top left, there's another figure that's like the sliding window of the convolution, and sorry, not the convolution, the filtering, uh, sliding window of the filtering. So that's, this is a 2x2 filter, or 3x3, or whatever is faster works. And on the figure 1A is kind of having the average pooling, the max pooling that I had on the code. Yeah. So these are the softmax and relo activation functions. So the relo on the figure 2 and the softmax is on the figure 2A. As you can see, relo is faster, goes linear, and the softmax, goes in that kind of shape. The model architecture, as you can see, this is an example of VGG16 convolutional neural network. You can see the image on the left kind of reduces, becomes, there's multiple convolutions in order to have a fully connected, layers here. So basically it uses many small 3x3 convolutions layers, and after each group of convolution layers, max pooling gets to resize the image, make it smaller, like I mentioned. So as the network goes deeper, the number increases here. It goes to up to 512. That's just an example. So yeah. So at the end of the feature, there's like a flattened the layers, and it goes to 3 fully connected layers to kind of have the final classification of the images. So here's the fully connected layer kind of explained. There's convolution, max pooling is also an example. It shows the input and output, and this is the neural network that the model works on. So there's a global average pooling, turns each feature map into a single number, and there's these numbers go into a 128 neuron dense layers, and every neuron is connected so the model can combine all features together. The final 10 class softmax layer in the Eurosat class is 0 to 9, as you can see, but we have like 128 for our example for CNN. So the experiment is based on baseline CNN, VGG, DNN, like I mentioned on the intro. These are the kind of models that I trained on. So the setup was kind of some data preprocessing on augmentation, training, validate, using Atom Optimizer and using the cross entropy and summary tables and stuff. And the performance kind of coming up with an increased consistency. And so the model kind of have a depth and architectural complexity. And so the result will be kind of having validation accuracy and, and loss. And then basically at the end we'll be comparing the results together. So here is the summary that we can generate from TensorFlow, and it shows on the bottom left there's trainable parameters, and over here on the custom CNN I had 111,000 kilobytes of trainable parameters. Some different models will have more trainable parameters and less depending on the architecture. On the right you can see there's 10 epochs, and the accuracy for the CNN was kind of around 89.70%, and as you can see the loss there's 0.3 loss. So yeah. Here's the result for accuracy and validation loss. As I mentioned, is 89%, and the loss is there. So the prediction is kind of having to predict residential set, sea lake, river, and stuff. And as you can see on the histogram on the left, is how many classes we have, each one kind of consisting around 2,000 images or so. So totaling up to 27,000 images. So the VGG16 kind of summary here, so only has 133 parameters, but it has a kind of pre-trained lightweight kind of parameters. It was 14.7 million, and this is kind of has accuracy, and it also reduces the image down from from whatever we like the technique uses. Here it uses 2 by 2 by 15 by 512. So the 512 is kind of the average pooling here to kind of have an accurate result. So after training, kind of reduces overhead, increases accuracy with this technique. So the result of the VGG kind of has multiple stages: stage one, stage two. There's, I froze the layer for the VGG. Kind of this improves the accuracy, and then the fine tuning it, and also improves the accuracy. And I was able to achieve here 93.5%. And yeah, with transfer learning. So this another model is ResNet 50 that I also worked on, and here you can see there's more trainable parameters. It's 527,000, so this takes longer to train. Here's the accuracy, and then kind of achieves around 93.5%, same as kind of VGG, and this is has kind of better generalization because it trains more, I guess. Efficient Net B0, that's the model, one of the model that I trained also, and it provides compact, strong kind of feature extraction. So meaning it has a small features while having only 4 million parameters, and this kind of had better accuracy as well. And let's see, this has a 91% accuracy when actually fine tuning and doing all those techniques, and I was able to get it to 91%. And this is the model for DenseNet 121 that I also tried, and this turns out to be the best model. And so this has small parameters and small trainable parameters and 7 million actual parameters. And for this, uh, let's see, I got 94.65%. It's one of the best models that I tried, and it learns fast and also strong, and it's consistent, as you can see, with multiple stages training. Um, the loss drops quickly and stays low, so meaning the model generalizes very well with a smooth, stable training curves. The last model kind of was the vision transformer, and this is the summary for the vision transformer. It has a lot of trainable parameters, and this is the accuracy for it, achieved 90.72%, and also this is one of the transformers that I've tried. Here's the comparison of all models, CNN, VGG, DNN, all these, and some of them were high comparison and high accuracy actually. Yeah. Here's like just a simple model prediction showing CNN and VGG, which one predicts better. Here is like around the same because they're like 90% above. So is there room for improvement? Kind of using a bigger size for training and applying stronger data augmentation. Um, Also trying newer models like efficient net v2 and performing some type of hyperparameters that can make it better for performance. Key takeaways is kind of the overall project. It showed the modern architectures and transfer learning based on the results on the satellite image classification from ERSAT, and each architecture has strengths and weaknesses. So CNN kind of was lightweight, VGG was stable, and so on. So the VIT captured global patterns kind of, and also fine-tuning pre-trained models improves the accuracy and reduces a lot of loss. And deep learning models can accurately, classify Eurosat images with strong performance. Thank you, everyone.